So, right now we are discussing basics of lasers, and slowly we are on our way to understand how to make pulsed lasers in the first place. As we know already, these 3-level systems often give you pulse lasing. 4-level systems by default would give you continuous wave lasing. But then we also said that Nd:YAG laser, for example, is a well known 4-level system, but then we do know about pulsed Nd:YAG lasers. So, which means we must be doing something by which the pulses are produced, they are not naturally pulsed. Similarly, titanium sapphire laser, which is the most commonly used laser nowadays for ultrafast studies, is intrinsically continuous wave. So, you have to do something to make them pulsed. So, what do you do something? What are the factors? That is what we want to learn. So, we will start our discussion today with continuous wave lasers, and then we will go on to pulse lasers gradually. And we will see that the same laser under some condition can have continuous wave operation, and if you tweak the conditions a little bit, you can get pulses. So, to start with, let us talk about a very well known continuous wave laser, a very well known and a very simple laser, that is helium neon laser, a HENI laser as it is commonly called. And I do not know whether you have seen a HENI laser yourself, because we do not really use it in our lab, but generally whenever alignment is required, HENI lasers are the default ones that are to be used, where you have huge lasers that you have to make, and then the high power lasers, you try and switch on the laser, everything might get burnt. So, what you do is you do the alignment using this laser. And if you go to our Raman microscope, there you will see there are two lasers. One of the two is a HENI laser. Now, in HENI laser what you have is you have this kind of a tube. We know by now that in a laser you have an active medium or gain medium, and you have two mirrors. These are this is the simplest way you can build a laser, right. That is what constitutes a laser cavity. So, as usual, you have one mirror which is a high reflector mirror, where reflectance is 100%, and you have another mirror which is partially reflective mirror. This is called what is it called? What is the partially reflecting mirror called in a laser? It is called the output coupler. Okay. You should also always answer, it does not matter, you may be wrong, but that is okay. Now, what you have here as an active medium is you have a mixture of helium and neon gases. Why mixture? We will come to that shortly. But it is important to remember that the ratio of helium to neon is 10:1, and for the record the partial pressures are 1 torr for helium and 0.1 torr for neon. So, why is helium present in 10 times the abundance of neon? We will see shortly. Okay. And then you have it inside a gas cell. One more thing I want to draw your attention to without explaining at the moment, we will come to it eventually, is look at how the gas cell is drawn. Generally, when we draw a cell, we like to draw a rectangle. Here what they have drawn is a trapezium. This figure is from Macquarie and Simon's book. Why is it a trapezium? Why are the ends of this gas cell at an angle that is not a right angle? And what is that angle called? That is a hint. That angle has a name. So, if you try to think of angles which have a particular name in context of optics, you might get the correct answer. Not magic angle in this case. Magic does not always work. It is some other angle. It is named after a scientist. It is called Brewster angle. Okay. Why Brewster angle? We will come to that eventually. Okay. And so, here you have the gas cell, where these are the windows basically. When I say the ends, the term that is used for them are windows, because light has to pass through them. So, we have all worked with cuvettes, and there we know that in a cuvette we have 4 windows, right. And in case of fluorescence cuvette, the windows are all transparent. In case of absorption cuvette, the 2 of the windows are transparent, 2 of them are opaque. Here we have 2 windows, and these windows are at a Brewster angle to the direction of propagation of laser light. And then you have this high current power supply, a high voltage power supply that is connected to it. So, what happens here? But before that, let me also tell you that you can actually generate different wavelengths from a Heine laser. You can get 3391.3 nanometer, you can get 1152.3 nanometer, and the most commonly used Heine laser that you will see gives you 632.8 nanometer. So, that brings us back to the application. I told you that Heine is one of the two lasers that are present in our Raman microscope. The other laser is Nd:YAG laser, which gives you green light 532 nanometer. By now, I think we know very well what the output wavelength of Nd:YAG is. What is the fundamental output of Nd:YAG laser? 1064 nanometer. Please do not forget that. 532 nanometer is not the fundamental output of Nd:YAG laser. We are going to talk about Nd:YAG laser later on, but please remember that it is actually an IR laser. You get 532 nanometer by frequency doubling. And this one, however, these are all fundamental emissions. 632.8 nanometer, which is the highest energy light that I have listed here, is also a fundamental light. It is not frequency doubled. When I show you the schematics, you will understand how this is a fundamental light. Okay? And the reason why Heine laser is used in Raman spectroscopy, can we say, can we guess why Heine laser is good for Raman spectroscopy? Yes, because of its higher wavelength. Higher wavelength is correct. Achha, so let us go back to basics of Raman spectroscopy. In Raman spectroscopy, you do not want, unless you are doing a resonance Raman, you do not want to have a transition to a next electronic level, right. You want to promote to a virtual level from which Raman scattering will eventually take place. So, you do not want too much of an energy. Of course, you can say what is the problem with using too much of energy? We might not still have resonance, and sometimes resonance is good anyway. The problem with using a blue laser for Raman, for example, is that you might have fluorescence that will compete with Raman. If you use a long wavelength, then this problem of fluorescence is eliminated. That is why in this Raman microscope we do have a green laser. It works for many of our samples, but red laser is the one that is preferably used, because there you eliminate the problem of fluorescence that can mess up your Raman signal if the fluorescence is strong. All right, but that was a little bit of digression. Let us come back to our main point of discussion. Heine can give you different wavelengths, but the same Heine laser usually would not give you all the wavelengths. If you want a 3391.3 nanometer laser, you have to make a dedicated 3391.3 nanometer laser. A 632 nanometer laser will not give you the other wavelengths. Why is that so? Let us see if you can understand, if you can arrive at the answer of this question by the end of this module. All right. So, now the thing is this, the way it works is that the first thing that this electric field does is it ionizes helium and neon. It strips the helium and neon atoms of their electrons, typically one electron. So, the ions are produced, okay, He plus, Ne plus, that is what we work with. So, that is the primary preparation of the species that are going to emit. Secondly, what happens is you produce the electrons, you have not really given the electrons just the escape velocity. You have produced high energy electrons that move at very fast speed. So, these electrons collide with ions and then transfer their energy to them, all right. So, remember when we discussed lasers earlier, we said that you can have different kinds of pumping. One way of pumping a laser is by using another laser, optical pumping. Here we are not doing that, we are doing electrical pumping, all right. So, it is important to understand the mechanism. So, what you do is you produce high energy electrons which collide with ions and transfer their energy to them. So, you have produced ions in their higher electronic levels, so to speak. In the second stage, what happens is an energy transfer takes place from helium plus to neon plus, and that is why you have to use a mixture of helium and neon. Okay. Remember, a two-level system will not give you lasing. You need 3 levels. You need to have population inversion. Okay. This population inversion is achieved by taking helium in excess, getting it energized, and then getting that energy transferred to neon which now has energy levels that are suitable to give you wavelengths that we just mentioned here. Okay. I will show you the energy level diagram, then hopefully it will become a little more clear. This is once again from Macquarie and Simon's book, the energy level diagram of Heine laser. So, see what we have here, we have helium, we have neon, this is the ground electronic state, singlet S0 state. This is a triplet S1 state, this is a singlet S state, all right. I do not know why S0 is written there, it should have been written something else, but let us not worry about that. Sorry, this S is not really singlet and triplet, this S has got to do with this term symbols, okay. So, you have a triplet state and you have a singlet state, and the meaning of 2s here is that what is the electron configuration of helium? 1s2 and helium plus would be 1s1. So, that electron has gone to 2s. Okay. So, that way you have produced this. So, now it is fortuitous, it is absolute, I mean no control over this, it is just that it happens that these excited states are close in energy to some excited states of Ne plus. This is not by human design, it just happens. So, when the energy gets transferred, it is very easy to populate these levels 2p5 4s and 2p5 5s. What is the meaning of 2p5 4s, 2p5 5s? What is the electron configuration of neon plus ground state? 2p5 only one electron is lost. So, what you see here is that electrons have been promoted to 4s and 5s levels. So, these are high energy transitions. Okay. So, this way what happens is you populate this and then you have other levels nearby, and this is why lasing action is so easy. You see, lasing is not taking place between this place and the ground state, that energy would be very high energy difference. Rather, there are many states, see there are 10 states each of 2p5 4p or 2p5 3p. You understand what I am saying, right? So, now that one electron is in 4p or one electron is in 3p. These are energetically close to this, and these are also higher energy states, right, not ground state. So, what will be the population of these 10 states or these 10 states usually? It will be 0, right, very high energy, right, compared to the ground state. These states are all at very high energy level. So, population is 0. So, that is why if you have even one Ne plus ion in this state, population inversion is achieved between this and this or this and this. If you have one Ne plus in 2p5 4s state, population inversion is achieved between 2p5 4s and 2p5 3p, right, and that is why you can get lasing, and that is why you get continuous wave lasing, right, because the final state to which the system goes as a result of the radiative transition, that state is has a population of 0 almost always. Okay. So, this is very much like your 4 level system, and here you get a CW output. So, Heine lasers that you have are all continuous wave lasers. Okay. Similarly, if you now go and see the argon ion laser, you can understand whether you expect it to be CW or pulsed, whether you expect one line or many lines. If you see ND laser energy diagram, I think you will be able to follow after this discussion. Okay. So, that is why before going into more complicated topics, it is better to discuss Heine laser at least once. All right. Yes.
Why is it going to 4s 5s? Is it just because their energies are closer compared to 3s?
Where?
The Ne plus.
Yeah. Yes. Exactly. So, that is right, because before going there it is easier for them to have non-radiative deactivation. Now, and I mentioned 3 lines, you might see that those 3 energies are actually all mentioned here. If it goes from 2p5 5s to 2p5 4p, these two are very close to each other, So, the energy is 3391.3 nanometer. 2p5 4s to 2p5 3p, you get 1152.3 nanometer. 2p5 5s to 2p5 3p, 632.8 nanometer. Also, there is something else. For the lower levels, this radiative transition is not all that favored. Transition moment integral is not, does not have a very large value. So, it is, to be honest, a serendipity that this helium neon mixture has all these properties that allow us to make a laser out of them. But it is important to take the mixture. If you just take neon, it may not be so easy. There will be many competing pathways perhaps, because there is no guarantee that these two levels will be populated to a very large extent. Okay, if you just take helium, of course, it will not work. So, it is a little serendipitous, but then it works. So, does anybody know when helium neon laser was introduced? Helium neon was one of the first lasers to be introduced, I think 1961 or 62, something like that, long ago. All right. Even now, many times you will see that you might think that now diode lasers are there, why do you want to work with helium? Because one problem of helium neon laser is that they go bad, because you are working with gases and you are working with something like helium, which wants to leak out of the vessel all the time. Diffusivity is very high. So, after a while helium neon lasers cannot be used anymore. Diode lasers have much longer time. So, in many applications Heni lasers have been replaced by diode lasers. However, the one good thing about Heni laser is that usually the modes are very nice. When I say modes, I mean transverse modes. That means, if you look at the laser on a piece of paper, it is a perfect circle and the intensity distribution is perfectly Gaussian. So, especially for microscopy applications, many people still prefer this. There are several other applications as well. Okay. But it is usually a low power Heni laser. You do get high power Heni lasers as well, but if you want to go to high power, Nd:YAG would be a better choice. Okay. Heni is good to give you red or infrared light in moderation. Okay. So, that is what it is. Now, from here when we go to pulse lasers, one thing that happens other than getting small pulses which are useful anyway is the amount of energy you pack into every pulse. That is a very major difference between pulse lasers and continuous wave lasers. Okay. So, before we start talking about how to make pulses, let us do this simple calculation, which I have made up the numbers to suit our titanium sapphire laser, and since I have made them up, it is very possible that I have gone wrong somewhere or the other. So, you people would better do the calculation as we go along. But roughly this is there in Macquarie and Simon's book for Nd:YAG laser. Okay. So, what we will do is, for our Ti-sapphire laser, I think we can more or less agree on these parameters. Ti-sapphire tsunami laser that we have in our lab, right? Power 0.8 watt, repetition rate is 80 megahertz, pulse duration is 200 femtosecond. When I say pulse duration 200 femtosecond, I do not mean full width of maximum, I mean 0 to 0, okay? Roughly 0 to 0, okay. And the 0 to 0 will become important very soon in some other discussion. All right. So, this is what it is. Can you calculate the energy per pulse? Power is given 0.8 watt. What is the meaning of 1 watt? Joule per second. So, all I am asking is, you have 0.8 joules per second and how many pulses per second? 18 to 10 to the power 6 pulses per second, very simple arithmetic. Total energy per second is known 0.8 joule, number of pulses per second is 80 into 10 to the power 6. I am asking you the energy per pulse, which means energy in 1 second divided by number of pulses per second. How much does it come to? Yeah? 10 raised to power? Cannot be minus 8. Is it minus? Yeah. Oh, this is energy per pulse. Energy per pulse is 10 to the power minus 8 joule. Is that right? Okay. Now, I will ask you another question. Can you tell me what is the number of photons per pulse? What is the energy of one photon? Energy of one photon. Well, one thing I have not written here is which wavelength, right? Let us say 800 nanometer. For our 800 nanometer photon, what is the energy? H nu, which is hc by lambda, right? So, this is also very simple. I know the energy per pulse. If I divide it by energy per photon, then I get number of photons per pulse, and that is, as you will see, is going to be a large number. So, 10 to the power minus 8 divided by h multiplied by c, and then in the numerator you are going to get lambda, which is 800 nanometer. I am asking for number of photons per pulse. 10 to the power minus 8 multiplied by 800 nanometer means 800 into 10 to the power minus 9, that is the numerator. Denominator is going to be, what is the value of h? 6.626 into 10 to the power minus 34 in SI units, multiplied by 3 into 10 to the power 8. Do not make it 10 to the power 10 like what I did few modules ago. 4 into 10 to the power 10 to the power? How can number of photons be 10 to the power minus 10? So, minus plus are very important, you do not get them confused. So, very large number of photons, right? 10 to the power minus 10 is a very, very small number. So, it comes to, so this is the number of photons you pack into one pulse. The reason why we are doing this is that very often we do an experiment or we learn something, but if we do not know the numbers at least once, if we do not work the numbers at least once, we do not really get the feel of what we are dealing with. Okay? So, it is important to get a feel of what we are dealing with. This is what we are dealing with in the laser that we have in our lab and that we have demonstrated during, well, we have not opened it up yet, now we are going to do it in a little while, not today, after a few days. So, there every pulse, we think 200 femtoseconds is such a small time. In that small time, you are packing 4.02 into 10 to the power 10 pulses. So, now think this light interacting with some matter. For a long time there is nothing, then there is an invasion. Within 200 femtosecond, this 4 into 10 to the power 10 number of photons are available to bombard the system, bombard all the molecules that are there, and that is something that can do things that cannot be done using a CW laser. So, what we are depending on here is large number of bombardments in a small amount of time. Okay. So, in chemical kinetics we have hopefully studied things like cage effect and encounters. So, what happens is you put things in a cage, then they hit each other many times and the reaction takes place. Here also what we are doing is we are packing a large number of photons in a small time, so it can actually get things done. So, that is the first thing that I would like us to understand today. But it is not over. Next thing, which is perhaps even more impressive, in case we have not got the picture completely yet, is can we calculate the radiative power per pulse? We know the power that we measure by power meter, that is the average power, that is 0.8 watt, 800 milliwatt, right, not much. Now, what I am saying is that, but what you see there is for most of the time nothing is there, you are seeing an average. So, how many pulses are there? For how much time, I have not written this, but you can work out. For how much time do we actually have the light on in 1 second? How many pulses are there? 18 to 10 to the power 6, and each pulse I am saying is 200 femtosecond. So, what for how many seconds within 1 second is the light actually on? 200 into 10 to the power minus 15 multiplied by 80 into 10 to the power 6. So, how many times? 80, say 100, 100 into 10 to the power, 100 into 10 to the power 6 multiplied by 200 into 10 to the power minus 15. How much does that come to? Does it come to microseconds? Okay. So, very small, right? So, this is sort of calculating the volume occupied by molecules of an ideal gas, right. Volume occupied by the gas is 22.4 liter if it is 1 mole. Volume occupied by the molecules is something really very small, right, nanometer cube or something. So, the light is actually on for a very small time, but whatever happens, happens within that time. So, now what I am trying to say is, if you now consider that time for which the light is on and leave out the dark period, then what is the power that you get per pulse? Can we do that? Radiative power per pulse. Energy per pulse is 10 to the power minus 8 and time for pulse we are saying 200 femtosecond, it is very easy. 10 to the power 4 watt, is it? 5 into 10 to the power 4 watt, right? So, that is very high, is not it? So, that is why when you use a femtosecond laser, it is very easy to damage your sample. Okay? That is why you can do things like laser cutting using this. That is a good thing. And that is why, if you remember, in our fog experiment, we keep the sample rotating. Why? Because the power that the molecules feel when the light is on is not 800 milliwatt. It is 5 into 10 to the power 4 watt. That is a lot. Okay? So, molecules will get fried very easily if you do not rotate the sample. Okay? So, very often we might not understand this. So, that is why we thought we will go through this calculation once. I meant to do it in the last module, time did not permit, but at least today we have been able to do it. So, it is important to understand that when you use a pulsed laser, even though the light itself might not look very strong, for the time when it is on, the force is, I mean the power is the right word to use here, power is really high. We will not understand it unless we do this treatment. That is why I wanted to do it once. But finally, what we have learned is, in pulse laser we are essentially subjecting our sample to very high power for short periods of time, and then of course, whatever application is there, that comes. Now, we come to the question, all that is very great, but how do we get pulsed laser? Okay? That is what we will take in the next module, and to do that we will need to understand something called longitudinal mode.